Okay, so our next area of proofs is going to be segments. And so we've worked on this before, finding different lengths, but now what we're going to do is we're going to prove these values, and we're going to prove certain characteristics, even if we don't have any numbers. So the first postulate that we have, and a postulate is really nothing more than an idea. It's a fact of mathematics that we follow, much in the way that a theorem is a fact that we follow. So segment addition postulate says that if B is between A and C, then AB plus BC is equal to AC. Here we can see that in picture format, where we have this segment AC, and we have B, point B, somewhere between those 2 points. That means that this segment AB, added to this segment BC, gives us the total distance. So let's say that AB is 2 and BC is 5, then AC is 7. That's the segment addition postulate, saying that 2 segments next to each other, added together, gives the entire length of the segment. So if we remember our 2-column proofs from before, obviously we have 2 columns, and the first column is going to be our statements, and the second column is going to be our reasons. And so what we want to do is we want to look at a proof, and here they actually give us a picture, and they say PR is equal to QS. And so this segment PR is equal to this segment QS. We want to prove that PQ is equal to RS. And this is a little bit tricky. So it's going to take some pieces, but we're going to go through it together. So PR is equal to QS, and that's given. So where do we go from there? Well, what we can do is we can say that PR is equal to PQ plus QR. Why can we say that? Because of the segment addition postulate. We have that this segment, this portion of the segment PR, which is PQ, plus QR, will give us the whole distance PR. So that means that we have the segment addition postulate. And actually in that same step, we could also say that SQ is equal to QR plus RS, or RS plus QR. Because here we have this SQ, or QS, is equal to QR plus RS. Now it's given that PR is equal to QS. And actually, if we remember when we talk about segments and lines, it doesn't matter the order that we write them in. So I wrote it as SQ. I'm actually going to change that real quick to QS because that's the format that was given before. So if I know that PR is equal to QS and PR is equal to PQ plus QR, and QS is equal to RS plus QR, can I set them equal to each other? Here, I used the substitution property. Now this is what we looked at before when doing algebraic proofs. So take a look back at those properties that we looked at before. Now if I have QR and QR on both sides, what if I subtracted them from both sides? If I subtracted QR from the left, I'd be left with PQ. If I subtracted QR from the right, I'd be left with RS. And I could do that because of the subtraction property. PQ is equal to RS, that's what I wanted to prove, so I'm finished with my proof. This was a little bit tricky, especially in visualizing that segment addition postulate and setting it all up. It takes time to go through these proofs. But take a look at this again. I would even recommend right now by yourself trying this proof again by yourself without listening or following along with the video and see if you can remember what to do. See if it clicks about what the steps that I made. All right, then we have some other properties here. So again, we have the reflexive, the symmetric, and the transitive property, which we looked at before, except now instead of talking about specific variables, we're talking about segments. So in this case, sides of this square. So we're going to write our two-column proof again. And I'm going to have my statements and my reasons. For my statements, I'm going to start with what's given. So I'm going to write this all out. So I'm going to say that wy is equal to yz. So for this square, wy is equal to yz. And I can see that 3 is equal to 3. Fantastic. I also know that yz is congruent to xz. So yz is congruent to xz, and xz is congruent to wx. Those are all given. I put them all in the same step. And so what I want to prove is that wx is congruent to wy. Here we can see it should be fairly obvious. I mean, it's a square, so these sides are going to be equal to each other. However, we need to prove that wx is congruent to wy. Well, we can see that wy is equal to yz, and yz is congruent to wx. So can't we say that wy is congruent to xz? And what we do there is the substitution property. Now technically we should say that wy is congruent to segment wy, because there is a specific difference between equals and congruence. For our purposes, we're not going to go too deep into that. So if you just want to write that wy is congruent to xz, that's absolutely fine. Now, if I have that wy is congruent to xz, I can also say that wy is congruent to wx, since wx is congruent to xz. And again, that's the substitution property. It's the end of the day. I cannot spell. So let's try that again. I can do the math, I just can't do the English. It's a problem. Okay. Now wy is congruent to wx. That's actually what I wanted to prove, so I'm done. I finished this in 3 steps. Not bad. It may seem obvious for some of these problems. And no matter how obvious, no matter what you're looking at, you can't just look at this point and say, it's a square. Of course they're equal to each other. You need to prove it. You need, just like a lawyer in court needs to prove his or her argument, you need to prove that wy is congruent to wx. And you do that using what you're given and the properties that we've looked at. One final proof here, or I guess 2 final proofs. This final proof here is we have a line segment, and AE and DB intersect. So it says draw a picture, so that's a great idea to help us out. So these two segments intersect at point C, and so I have AE and BD. I want to prove that AC is equal to CD. Now, for my first statement here, I'm going to have all that's given. So C is midpoint of AE. C is midpoint of BD. And AE is equal to BD. If you remember when we looked at midpoint before, that means that it cuts them equal. So we know that AE is going to equal CE. We also know, and we can say that this is because the definition of a midpoint. We can also say in the next step that BC, BC is equal to CD. In the previous step, I wrote AE. I meant to write AC. AC is equal to CE. BC is equal to CD. And again, that's definition of the midpoint. Well, if I know that AC equals CE and BC equals CD and AE equals BD, that means that AC plus CE is equal to BC plus CD. And that is the segment addition postulate. Now to get that AC is equal to CD, I can subtract CE and BC from both sides. But since I know that CE is equal to BC, I know that AE is equal to BD. So that means that AC is going to be equal, CE is going to equal, BC is equal to CD because of the definition of a midpoint. Then I can use segment addition postulate. I'm trying to get to AC is equal to CD. I should have said that these two are equal to each other first. This is tricky here. Can you guys see what's going on? Well, I'm going to say this is going to be the subtraction property, and I'm going to come back to this one. But the key here is using your substitution and using your definition of a midpoint. So while definition of a midpoint is not specifically a property we covered, we did cover midpoints. And anything that you've been taught is fair game to use in a proof. All right, then this one here. Again, we want to draw another picture. Hopefully this helps us out this time. So in triangle J and L, so J and L, there's a lovely triangle. So J and L, we know that LK is equal to, K is a point on JL. So there's point K. We know that LK is equal to NM. Point M. Point M is on JN. Okay. So KL is equal to NM, and KJ is equal to MJ. So we want to prove that LJ is equal to NJ, that those two sides are equal to each other. Well, let's start with the given. And so I'm going to say that LK is equal to NM, and KJ is equal to MJ. All right, so since LK right here is equal to NM, well, actually, what I'm going to do is this. I'm going to use segment addition postulate. So I'm going to say that LK plus KJ is equal to LJ, and that's the segment addition postulate. And I can do that again for the other side, and I can say that NM plus MJ is equal to NJ. And again, that's a segment addition postulate. Okay. Now, knowing that LK is equal to NM, I can use that in sort of a subtraction piece. So I can say, and I can use substitution. So LK is equal to NM. That is given. So notice how this equation has an LK and this equation has an NM. What if I wrote the first equation in step 2 as LK is equal to LJ minus KJ, and then also wrote the equation in step 3 as NM is equal to NJ minus MJ. And that would be because of the subtraction property. So in both step 2 and step 3, I subtract it from both sides. In step 2, I subtracted KJ from both sides. In step 3, I subtracted MJ from both sides. Now, it's been given to me that LK equals NM, so I can use substitution to say that LJ minus KJ is equal to NJ minus MJ. And this was because of the, again, substitution property. And finally, it was given to us that KJ is equal to MJ. So here's KJ and MJ. So if I add those values to both sides, they're equal. And so they cancel out. So that means I get LJ is equal to NJ. And that's the addition property because I'm adding equal values. And I get my proof. So to recap, I'm given that these two portions of the segment are congruent to each other. So I use segment addition to create an equation in steps 2 and 3 for each of these sides using the smaller segments. Using substitution, I set those two sides, using subtraction, I isolate LK and NM. Using substitution, I set those two equations equal to each other. And then using addition, I add the congruent values. Again, try going through this by yourself separately without the help of the video and see if what you did matches. See if you can remember the pieces that I just did. And for this previous one, that's actually how we should have gone about that. So, tell you what, why don't I take the time right now and I will go through this again. So we start with what we're given. And so for number 2, if C is the midpoint of AE, then that means that well, we know that AC plus CE is equal to AE, and BC plus CD is equal to BD. This is the segment addition postulate. So if we look now, it's given that A equals BD. A equals BD. So that means that AC plus CE is equal to BC plus CD. And this is the substitution property. Okay. Now we want to get to AC is equal to BC. AC is equal to CD. So how do we prove that CE is equal to BC? Well, we know that AC plus CE is equal to AE. Don't we also know that AC is equal to CE? And we know that because of the definition of a midpoint. We also know that BC is equal to CD because of the definition of a midpoint. So this is the part that I was missing before. If I replace CE with AC, I get AC plus AC. AC plus AC, which is 2AC. And if I replace or substitute BC with CD, I get CD plus CD, which is 2CD. And so that is the substitution property. And finally, for number 6, I can use the division property because I have these values of 2 on both sides. So if I divide both sides by 2, I get AC is equal to CD. So sorry, that one tripped me up from before. But you can see that, even me, I can get confused with this. This can be tricky. So the important part as you go through this is really set out a plan. Think through this. If you need to do this one time and then erase it and go back to it, or do scratch work on a separate piece of paper, then do that. You're going to make mistakes with these, and that is absolutely fine. I would recommend that you go through these proofs again and you try to do them now that you've seen me do it, and pick up and take note of where you get confused. But for the proofs, it's really just a matter of thinking. So make sure you give yourself the time to think.